What is the purpose of a re-ranker in an advanced RAG pipeline? The answer is option C. Picture a recruiter using a fast keyword scanner to cut 10,000 resumes down to the top 100. Quick but rough. Then a senior hiring manager actually sits down and carefully reads just those 100 to pick the real top 5. First pass is fast and coarse. Second pass is slow but precise. And it only works because the first pass already narrowed the field. That's exactly what a re-ranker does. Vector search is fast because it uses lightweight math across millions of chunks. But that speed costs you precision. Some near misses can rank above genuinely better matches. A re-ranker takes just the top 20 or so candidates and rechecks each one much more carefully against the actual query, comparing them side by side instead of as a separate floating vectors. Why not run this heavy checker on everything from the start? Too slow. Same reason the hiring manager can't personally read all 10,000 resumes. So you get a funnel. Fast and rough first, slow and precise second. And that combo noticeably boosts answer quality. What problem does chunk overlap solve when splitting documents? It's option A. Imagine reading a mystery novel, and right at the most important line, the killer was revealed to be. Someone rips the page in half. You're missing the one thing that mattered, purely because of where the tear happened to land. That's the real risk with basic chunking. Split every 300 words with a handcuff, and you might sever a sentence right at the boundary. Chunk 5 ends with the warranty does not cover damage caused by. Chunk 6 starts with water exposure or drops. Ask does the warranty cover water damage? And if only chunk 5 gets retrieved, the answer looks completely wrong. Not because the info didn't exist, just bad timing on the cut. Chunk overlap fixes this by letting consecutive chunks share some text. Usually, the last 10 to 20% of one chunk repeats as the start of the next, so that crucial line about water damage ends up fully intact in at least one chunk. Bit of redundancy, sure, but it guarantees nothing gets cut in half by bad luck. What is query rewriting used in for advanced RAG? The answer is option D. Think about how you would phrase something to a friend versus a search engine. To a friend, you might say, my thing keeps crashing. Any idea why? Vague, full of context they already have. Type that into a search engine and you get garbage because my thing and crashing alone don't retrieve anything in specific. Real user queries are often exactly like that. Query rewriting uses the LLM itself as a first step before touching the vector database. It asks, given the conversation so far, turn this vague question into something clear and self contained. So, why does it keep crashing? Becomes, why does this XYZ app crash on startup after the latest update? Way more useful for search. Query expansion goes further. Generate 5 different phrasings of the same question. Search all 5, then merge the results. Like asking 5 friends to independently search using their own words. One uses jargon, one is casual, and between all 5, you are way more likely to hit the document that happens to use that exact phrasing. What role does metadata filtering play in a production RAG system? The answer is option C. Imagine a hospital's knowledge base, treatment protocols, HR policies, financial reports, all mixed together. A nurse asks about a dosage protocol, and you really don't want the search accidentally pulling up an outdated 2015 version, or a finance only document, or worse, a patient file that they are not clear to see. Metadata filtering tags every chunk with structured info at index time, date, department, access level, document type. At search time, the system filters first. Only search cardiology documents dated after 2025 accessible to nurses. Then it runs the meaning based search inside that already narrowed pool. Without this, pure semantic search treats everything as equally eligible just based on meaning, which creates real problems. security leaks where a low access query accidentally surfaces something it shouldn't, or staleness where an old policy outranks the current one just because it happened to phrase things a certain way. That's why basically every enterprise rack system, legal, healthcare, finance, layers this filtering on top. How do you actually evaluate whether a rack system is good? Which metric pairing matters the most? The answer is option A. Grading a student's essay, you would check two separate things. Did they cite good sources at all? And separately, even given good sources, did they actually stick to what those sources said? A student can nail one and totally fail the other. RAG evaluation splits the same way. Retrieval evaluation asks of what got pulled back, how much was actually relevant. That's precision. And of everything relevant that existed, how much did we actually find? And that's recall. Great recall but poor precision is a librarian handing you 50 books where only 3 are useful. Great precision but poor recall means you got 2 perfect books but missed 8 other genuinely relevant ones. Generation evaluation is separate. Given the chunks the model actually received, did it stay faithful to them or add stuff that is not actually supported? Usually checked by having another LLM act as a judge. And here's the scary part, a system can have perfect retrieval and still give a bad answer if the generator just ignores what it was handed, which is exactly where we are headed next. Even with perfect retrieval, why can a RAG system still hallucinate? And the answer is option D. Here's an uncomfortable truth. Handing an LLM the right facts does not guarantee it actually uses them. Imagine an expert witness in court handed a document that clearly contradicts what they already believe. Some witnesses read it and update. Others skim it and just testify their old belief anyway, despite holding the correct document the whole time. LLMs can act like that second witness. Sometimes the model's deep training time knowledge overrides the freshly retrieved fact. Say the retrieved document says a law changed last month, but the model was trained on years of the old version and it just defaults back. Other times, the retrieved chunk is only loosely related, past the retrieval stage, but does not actually contain the specific answer. And instead of saying, I don't know, the model fills the gap with a confident sounding guess mixed with real facts, which is honestly more dangerous because it looks well sourced. And sometimes it just misreads the document, like skimming an email and misremembering a number 5 minutes later. This is exactly why faithfulness checking exists separately from retrieval quality. Good retrieval is necessary, but not even close to sufficient. What is multi hop or agentic RAG, and why is it needed for certain questions? The answer is option C. Try this question. Which company acquired the startup founded by the person who used to lead engineering at the company that made the first iPhone? No single document has that whole chain. You would need to find who led engineering at Apple, then what startup they later founded, then who bought that startup. Three lookups, each depending on the last one. One vector search can't do that at a single shot. That's multi-hop or agentic RAG. Instead of one retrieve then generate pass, the system works like a detective. Retrieve something relevant to step 1, read it, use it to build the next query, retrieve again, repeat. The agentic part is the model deciding after each step, do I have enough yet or do I need one more search? Same as a detective deciding whether they have got enough evidence or need one more witness. This is completely different from the simple one shot RAG we covered earlier. Great for direct lookups, hopeless for chained questions. The cost is speed. Multi hop might mean 3 to 5 retrieval rounds instead of one, so it's usually reserved for genuinely complex questions. In a vector databases, what's the actual trade off between an algorithm like HNSW and brute force exact search? The option is answer A. Say you want to find the closest friend's house out of a million addresses by literally driving to every single one and measuring. That's brute force. Guaranteed correct, but painfully slow. Now imagine a rough map with shortcuts between neighborhoods. You quickly narrow down definitely somewhere in this district, then only check carefully within it. It's way much faster, but there's a small chance a house right on the edge of the next district actually was closer and you missed it. That's basically HNSW, a graph structure built during indexing, connecting vectors to their approximate neighbors at different zoom levels, like a highway system feeding into local roads. Search starts on the highway, narrows fast, then drops to local roads for fine detail. The catch and why it's called approximate nearest neighbor search is that speed comes from not checking everything. So occasionally you get the second or third closest match instead of the mathematically perfect one. In practice, the tiny accuracy loss is invisible to users, while the speed gain is the difference between instant answers and a multi second wait, even across billions of vectors. What does self RAG or corrective RAG add on top of the standard retrieve then generate pipeline? The option is answer D. Think about a junior writer who takes whatever research they are handed and just writes the article no matter how thin the sources are, versus a seasoned editor who pauses and asks, wait, are these sources actually good? Am I forcing this quote in? Should I go find better material first? That self check loop is exactly what self RAG adds. Standard RAG is rigid. Retrieve once, generate once, done. Even if what got retrieved was mediocre. Self RAG inserts checkpoints. After retrieving, the model asks, is this chunk actually relevant? And can throw out the ones that are not. After generating, it asks, is my answer actually backed by what I was given? And if not, it can retrieve again with a better query or just flag that as unsure instead of confidently guessing. Corrective RAG is a close cousin. A lightweight evaluator scores the retrieved documents as good, ambiguous, or bad. And if they are bad, the system falls back to a broader search, even live web search, instead of forcing an answer from weak material. Basically, RAG growing up from an assembly line into a careful researcher that double checks itself. What is GraphRAG and why might it outperform standard vector based RAG for certain questions? And the answer is option C. Take a question like summarize the connections between company A, its three subsidiaries, and the lawsuits each one's involved in. Standard vector search finds chunks that sound like the question, but the real answer needs you to connect the dots across many separate documents, one about ownership, another about filings, another about settlements. Vector search does not actually know that subsidiary X is owned by company A. It just knows both phrases show up in similar sounding text. GraphRAG fixes this by first extracting entities, people, companies, events, and the actual relationships between them, building a real knowledge graph like a family tree but made of facts instead of family members. When a question needs multiple connected entities, the system walks the graph directly from company A along its owns edges to each subsidiary, then along involved in edges to each lawsuit. It's the difference between flipping through a pile of loose photos versus having an actual family tree in front of you. GraphRAG shines on questions that need synthesis across many documents, where the answer never sits whole in any single chunk, which is exactly where plain similarity search structurally runs out of road, no matter how good your embeddings are.